This video discusses how you would go about completing one of the assignments on my PLTW associated with the first class lever. It is an assignment that is in the so-called distance learning section, and this is a companion to that activity. And you can see it has the standard sort of header associated with distance learning. We come through here and it identifies itself as a companion to the my PLTW stuff. And instructions are follow the directions in the table below to help you complete the assignment. All steps refer to those at this page on my PLTW. So what is that page? Well, it is this one here. So it's the Part 1, First Class Lever Examples, Distance Learning. So if we come back here, let's just go through this. So steps 1 through 6 you're going to do as instructed on my PLTW. And that's basically just reading and watching some of these. I think there's not a little video yet. That's, yeah, number 6. There's a little video. You'll watch that. And as shown here, there's a whole bunch of resources that they want you to pull up and review. There's slides 1 through 23 of the presentation on levers. There's a link to a discussion of generic properties about simple machines, all of them. There's a CAD model, which you'll need to access. CAD model of a first class lever on Onshape. And finally, this link, which talks a little bit about Onshape. Okay, so you'll want to be sure and click all of those links and pull that stuff up. So let's come down through here, and basically it says, okay, you got a first class lever. This is what it looks like in real life. If we were to be on campus, we would build it, and it would look something like this. This is what it looks like if you build it in Onshape. And here's the video where the person demonstrates that we have a first class lever, and we just pull down on the force sensor, and we oppose the force associated with gravity pulling this 1 kilogram mass down. And this device is wirelessly communicating what it measures in terms of the force required. So this measures the effort force. Okay. Then we get to number 7, and they ask us to calculate the ideal mechanical advantage. And for this one, they give us a little spot here to fill that in. You're going to do this on a piece of paper. So it says what formula you're going to use, substitute and solve, and give the final answer. And to do the ideal mechanical advantage, you'll recall that that's going to be the ratio of the effort distance divided by the resistance distance. And so what you're going to need to do is measure for this little model here those quantities. So if you click up here and pull up that first class lever, here it is. And what you're going to have is a situation where, as they discuss, you can either count the number of squares from the fulcrum. The fulcrum is right here, and the force sensor is placed right here. So this is going to be F sub E right here, and this is F sub R, 1 kilogram. And so you can just count the number of squares on each side of the fulcrum and divide those numbers of squares over here divided by the number of squares over here. That'll work since we just use ratios. We can also get a little fancier and try to use this tape measure here on Onshape. I'm going to demonstrate and try to convince you how it works. So if we come up here and look at one of these, let's say one of these squares, if I click right there and then right there, nothing happens. So if we click here, well, the way it's supposed to work is that if we click on some location, like say right here, okay, it looks like that was the second measurement. So you click once, you get the measure, the dimension of that object. You click the second time, you get the distance between the first 2 clicks. So what I'm going to do here is measure from right here over to right here. So I'll click here, and then I'll click there, and then back over to here. And let's see what it gives us. This is kind of hard to decipher. So it's got a minimum distance of 5.9 inches. And that's along mostly along the y direction. And if you look up here on the view cube, you can see that the y direction is horizontal here. So basically those 2 points differ by about 5.9 inches in this direction. So that's about the size of the moment arm. They also differ in the Z and the X directions, but we don't really care about that. Z being up and down and X being into the paper. So this is one way you can play around with this, one way to measure things. It's a little fussy, but it's a little more high-tech, if you will. Or again, you can count the number of squares, and we can go from there. So let's come over here, and once we get a measurement there on number 7, it says calculate the ideal mechanical advantage. Well, I'm going to assume that the ideal mechanical advantage is given by, let's see, there we go. Alright, so you're going to do this on a separate piece of paper. So you're going to say something like activity 1.1.1, and I believe that is just generally levers. Let's see, I'm going to get the, yeah, so this is levers, and we're doing part 1 of a first class lever. And sorry about that, I'm not showing what I'm writing, so I just wrote this. Okay. Now what it asks us to do is to draw a picture and to annotate it and things like that. Normally I would definitely do this in pencil, but I'm going to do it in marker so that it appears a little better. So there's our fulcrum. So let's label that. Remember, we want to label everything that we draw. And this is first class lever. It has a equal moment and resistance arms, if I'm not mistaken. So I'm going to go ahead and maybe go, let's see, I want this to look nice. So I'm going to go, let's say 6 there, and then another 6 there. And maybe I even give it some, again, you're going to be doing this in pencil, probably. And again, I'm only doing it in marker because I want this to be very visible. And let's see, we had the resistance was going that way. Resistance force was going down. And the effort force, you'll recall, was also going down. So, okay, that's going to give us a little bit of confusion. This is F sub E. So what's going to happen is that the whole thing is going to start to rotate in a counterclockwise direction. So while F sub R is the 1 kilogram mass, we're better off drawing it like this. F sub R going up, because we want to illustrate the force that we create by pushing down here with F sub E. It's going to go up, and they're equal. It's equal to 1 kilogram just as we start to move it. So these are equal in magnitude right as we start to move it, or they're equal in magnitude as we move at constant speed up. Bottom line is that when we push down with F sub E over here, we get F sub R going up over there. Alright, well, this is D sub E, and this is D sub R, and we've convinced ourselves that the ideal mechanical advantage is the ratio of those two quantities. That's why we could use any method of measuring them, number of squares, or actually measuring them with the tools in Onshape. Now let's just say, for the sake of argument, that that is a true, is a first class lever which has equal length moment arms. And so I might say this was something like, let's just say it was 5.9 inches and 5.9 inches. So I would get, an IMA of 1. So I wouldn't amplify the force, however I would change its direction. So that would be number 7 if D sub E is equal to D sub R. It may be, it looks like it's pretty close, but you're going to measure it to find out. So keep that in mind, if D sub E is equal to D sub R. Alright, and you'd put your name right here, and class, so this is what, POE. Let's say this is POE second period, and this you're going to put your name there. There we go. And let's go on to see what else they're asking us. And again, I always have to go back to this because I find that the MyPLTW is pretty wordy at times. So we've got number 7. Let's go back there. As we come down here, let's see, 7. Okay, we did 7. Now we want to do 8. Calculate the ideal effort force needed to overcome the known resistance in force in example A. So that would be number 8. So let me make sure that this is visible. We'll come along here and say number 8. And you'll recall also that if we don't have any friction, IMA is equal to the resistance force divided by the effort force. This is with no friction. Alright, so let's read 8 again. Calculate the ideal effort force needed to overcome the known resistance force. Okay, so the known resistance force. Let's see. I'm trying to remember what GUPPY stands for. Given unknowns. Picture, maybe? Somewhere we need the equation in there. And then maybe insert. I think I completely blew that one. Bottom line is that let's go systematic with this. And let's say, what are we given? Well, we're given that the resistance force is associated with 1 kilogram. And therefore, we know that F sub r is going to be the mass, 1 kilogram, times the acceleration due to gravity. And that's going to be 1 kilogram times 9.8 meters per second squared. Darn it. I got to keep looking over there more. And so that's going to be just 9.8. And I'll be very explicit with kilogram meters per second squared, but 1 kilogram meters per second squared we give the name Newton. So F sub r is equal to 9.8 newtons. Okay. And what's the unknown? Well, if we come back here, the ideal effort force. So F sub E is the unknown. Okay, so we have our given, we have our unknown. And if we come back up here, they say, okay, in example A. So for that one, I have to assume that also, in terms of given, we have that the IMA is equal to 1. So that's given, and that's given. And the equation is IMA is F sub r over F sub E. So then we can rearrange that to get F sub E is equal to F sub r over IMA. And for a simple first class lever with equal moment arms, it's not very 9.8 newtons. It's not very interesting, right? Because IMA is just equal to 1, so they're equal. 9.8 newtons, so we'll write that off in a little equation here. The ideal effort force is 9.8 newtons. And so it's the same. So that would be number 8. Now let's go and take a look at 9. To find the actual effort force in example A, analyze the video or the data file. And if you'll recall, I asked you to come over here and use a different data file. And that data file is right here. So if you click there, you'll get this data file. Now, interestingly, let's see. Yeah, okay. So the data file here, as you can see, kind of makes sense. It does make sense. Let's make it a little smaller so we can see it. And so that force sensor will be on 0, and then we start to pull on it, it goes up, and then it sort of saturates out here. And we're going to choose the maximum value. They tell us somewhere in the instructions to do that. So to get that, I want to show you how to do that, if you don't already know. And I'm going to put it right here. So max force in newtons. And I'm going to use an equation equals max, left parentheses, and then I'm going to grab all this data here. Okay. And I can just hit enter, or I can put the right parentheses. It'll add the right parentheses if I don't add it. So we get something like that. Let's cut down on some of the stuff coming out over there. It's about 9.9, let's say. So the maximum value of this data file, which is similar to the data file we would find if we were on site working, is 9.9 newtons. So let's go back to our map here. Okay, so it says do it the same, but use a different data file. Now let's go here, number 9. It says find the actual effort force. The actual effort force. Yeah, we just did. So let's do that. So number 9, actual effort force F sub E, you can just say by inspecting the data and graph and choosing the maximum value, we find that, yeah, F sub E is equal to 9.9 newtons. Okay, let's come back to our map here. It says, okay, we've done 9. 10, 11 are on paper, so let's go take a look at what they say. Number 10, calculate the actual mechanical advantage. Well, let us do that. The actual mechanical advantage, let's do it right here. This is number 9. The actual mechanical advantage. We know that AMA is only obtained when we actually measure the force, and that's in this ratio. So we just measured the actual effort force, and that was 9.9 newtons. And I think we decided that this was 9.8 newtons. The resistance force, which was just 1 kilogram. We got that because we know that it is 1 kilogram, and a mass of 1 kilogram in the Earth's gravitational field is pulled down with a force of 9.8 newtons. Okay? So our actual mechanical advantage appears to be very close to 1. And I'm going to, let's see, find a calculator somewhere. I can't find one, so I'm going to come up to my spreadsheet and just use that. So that's what, equal 9.8 divided by 9.9, and it's about 99.99, 0.99. So AMA is 0.99. So that's a pretty well put together. Sorry, you didn't see me do that. That's a pretty well put together lever, well lubricated or good fitting parts. So again, the resistance force is just the force of gravity associated with 1 kilogram mass, 9.8 newtons. The effort force we determined from the graph. We chose the maximum value, and it's 9.9, so we get that. And the ratio is just 0.99. Finally, I think we have one more to go. Maybe a couple more. There's 10 and 11. I believe actually this was... I believe this might have been 10, but I'm not sure. So let's just do 11. So let's go to 11. Calculate the efficiency. The efficiency of that thing is, so 11, the efficiency, we gave it this kind of funky E is equal to AMA over IMA times 100%. And so we can immediately see that, well, I guess not immediately, 0.99 for the AMA goes there. IMA, I believe, we convinced ourselves that it was 1. We did. And again, when you measure the things, they will probably be different. And so times 100%, so we get E is equal to 99%. Or at least I do. Okay? Let's go further and see what we need to do. So 12, consider, okay, so that's it. We're finished. This one, yeah, 11. So what we've done is we've done an experiment using this device, which we normally would build in the lab and measure with actual force sensors. However, we're mimicking that by measuring on the CAD model. So that is how you would proceed with that. And also, then you would take a photograph or scan your work. If you scan it in as a PDF, just submit it to Google Classroom with that name. If you took photos, you'll want to put those photos in a Google document and name that appropriately and put that into a Google Doc. So let's see, let me emphasize here, do not submit image files. So I want you to insert those images into a Google Doc. Alrighty. Now we'll move on to the second class lever.